Hello, we are back. This is our final unit, Unit 8, which is all about vectors. This is Mr. Boothman, and I'm going to be taking you through section 8.1 right now, which is just a basic introduction to vectors and a few of the basic operations that we can do with them. So we'll start by talking about vectors, but before we talk about vectors, we need to talk about something called a scalar. So a scalar is actually something that's really common that we've been using a lot, and it's just a measure of something's magnitude. So it's any quantity that we can represent using just a single number. So some examples of that include weight. We can talk about length. We can talk about something's area. We can talk about a temperature. Like there's a bunch of different values that we can describe using just a single number. And in fact, most of what we do in math and science deals with scalars. But sometimes we want to talk about uh, things that not only have a magnitude, but they also have a specific direction. And that's a vector. So yes, just like Despicable Me. A vector tells us the magnitude as well as the direction of something. So not only do I know the length of a line segment, I know the direction it's pointing in. Not only do I have a speed, I know which way I'm traveling at that speed. Things like that. So vectors are really useful, obviously. Like we talk about speed and direction all the time, especially in physics. Um, and so this whole unit's about building our familiarity with them. So two vectors are considered equal if they have the exact same magnitude and direction, as you can imagine. So if they have the same length and they're both pointing in the same direction, they're equal. They're the same. And another way of thinking about a vector that I think is going to be more useful to us throughout this unit is to think of a vector as a measure of displacement. So if I'm talking about a velocity, which is both speed and a direction, um, I'm talking about my total displacement. So if I'm traveling at 75 miles an hour going north on the freeway, then my total displacement is going to be where I started and then where I ended. That's my displacement. And so for that reason, we can think of the zero vector, which is just a big zero, it's bolded, as representing no displacement. So if we're not moving anywhere at all, that's the zero vector. That's what a zero means in terms of vectors. Now, in general, when we see vectors, we do bold like this, the V, or whatever letter we happen to be using. And then we use these special pointed brackets. And that's to let us know that we're talking about a vector as opposed to any other value, a point or something else. And here in our brackets, a vector has two pieces, at least in two dimensions. We have a horizontal component and a vertical component. In other words, we have a horizontal displacement and a vertical displacement. That's A and B, respectively. So if I ask you to sketch the vector for 8, then 4 is my horizontal displacement over 4, and then 8 is my vertical displacement, up 8. That was really bad. Sorry. And so from where I started to where I ended, that's the vector. That's my total displacement. This is V, with the arrow showing the direction. So this was 4, this was 8, this was A, my horizontal displacement, and this was B, my vertical displacement. Now the special thing about vectors as opposed to any other line that we might draw is that, like we said up here, two vectors are equal if they have the same magnitude and direction. So I could draw this same vector, but instead maybe I start here. So I go over 4, and then up 8. And now that's my vector. I have the exact same A and B, but I started somewhere different and I ended somewhere different. It doesn't matter. It's still the same vector. So I could draw this anywhere on this coordinate plane, actually, as long as my horizontal and vertical components, the displacements, are 4 and 8. So we can talk about how to find a vector. So if I wasn't given the horizontal and vertical components, if instead I just told you, what's the vector that goes from 1, 0 to 10, 5? Well, you would probably tell me, well, that's 9 and 5. So how do we do that? How do we find that total x distance that I traveled and then the total y distance that I traveled? It's just subtraction. So in general, if I have a vector v, and I know that it starts at the point x1, y1, and it ends at the point x2, that should be x2 there, y2, then the vector is just x2 minus x1 and y2 minus y1. And note that it is important that we start with the x2 and the y2. Since we have direction, if I were to start with x1 and y1, it would be a little different. So x2 minus x1, y2 minus y1. So looking at a quick example, find the component form of the vector u with initial point 1, 2, and terminal point 10, 8. So here's my vector. Here is my B, and here's my A. So U equals 10 minus 1 and 8 minus 2. 9, 6. And if we check and we count these squares here, that is in fact 9, and then this is 6. So component form of vector, really easy to find, really simple and straightforward, I think. But a natural question that comes from looking at this picture here, what shape did we just make? That's a right triangle. There's a reason we do this after trig. I might ask, well, what is the length of that vector? What is the length? What's the total distance that I traveled? Well, when we're talking about vectors, that is the magnitude, the length, or whatever other value we're representing here. So the length of this vector, or the magnitude, well, that's just going to be the Pythagorean theorem. A squared plus b squared equals c squared, or if I take the square root of both sides, that side length, the hypotenuse, is going to be the square root of a squared plus b squared. And we do use these absolute value bars to denote the magnitude or the length of a vector. Now, I just want to pause and take a second to appreciate all the different names that we have for finding that distance, right? We call it distance. We call it the magnitude here, the length of the vector. It's the absolute value, or the modulus, if we're talking about complex numbers plotted in the complex plane. It's the hypotenuse of this right triangle. It is r, if we're talking about angles and trig functions. But it's all the same formula. It's all exactly the same thing. It's the distance, the absolute value. So finding the magnitude of each vector really couldn't be simpler. So again, we use the absolute value bars here. Square root of a squared plus b squared. Square root of 4 plus 9, square root of 13. And again, it's positive. We don't get a positive and a negative value because this is distance, it's absolute value. It's only positive. My magnitude has to be positive. So the magnitude of this second example here, square root of a squared plus b squared, that's the square root of 25 plus 0, square root of 25, which we know is 5. And then finally, the absolute value of w here. It looks a little worse, but I promise it simplifies nicely. Square root of 3/5 squared plus 4/5 squared. So the square root of 9 over 25 plus 16 over 25. It's the square root of 25 over 25, which is 1. It's really nice and straightforward. And we are doing plenty of practice with this in class. And I'll make sure to post some of those problems that we do later on. So the last part of this section, and again, like I said, this is a pretty straightforward section. I think it's pretty simple, is talking about the algebraic operations that we can perform on vectors. So things like adding, subtracting, and multiplying vectors by a number. And in this case, we're multiplying vectors by a scalar, like a single number. Thinking about vectors as displacement makes this pretty straightforward. So if I am talking about two separate displacements, u and v, two different vectors, like here, then when I add them together, do this displacement and then the second displacement, that's really just the same as a single displacement from where I started to where I ultimately end up. And to find that displacement, I'm taking the first horizontal displacement and then adding the second horizontal displacement, the first vertical displacement, and then adding the second vertical displacement. Same with subtracting. So if I want to think about a negative vector, if a vector has area, or not area, direction, then when I'm taking a negative vector, I'm just flipping it. I'm turning it backwards. So thinking about u minus v is the same as saying, well, what if I displace something, the first vector, u, and then I'm adding in that second negative displacement, negative v, going backwards, and that's what we get here. And again, I just end up subtracting the horizontal displacements and subtracting the vertical displacements, the components. If I'm multiplying a vector by a scalar, well, if I multiply it by half, I'm just cutting that magnitude in half. I'm cutting the length in half. Multiply it by 2, I'm doubling the length. Negative, again, flipped it. And then any combination of that, a negative fraction, a negative whole number. So in general, if I have two vectors, a1, b1, and a2, b2, those are my horizontal and vertical displacements, components, and then c is some scalar, some number, then to think about adding u plus v is just adding the horizontal components and then adding the vertical components. Subtracting u minus v, that's subtracting the horizontal components and subtracting the vertical components. And then a scalar, multiplying by a scalar, it's just multiplying each component by that scalar. So really, really straightforward, I hope. Let's go ahead and work through a few examples. So u plus v, this is u, this is v. That's going to be a1 plus a2, so I find it helpful to label my points, or not points, my components. So that way I know exactly what I'm plugging in. So a1 plus a2, that's 2 plus negative 1, and b1 plus b2 is negative 3 plus 2, which is 1, negative 1. That's u plus v. So what that's saying is that my total displacement ends up being 1 over 1 to the right in the positive direction, and then down 1. That's the total displacement I end up with after doing both u and v. If we look at u minus v, that's a1 minus a2 and b1 minus b2. 2 minus negative 1 is 2 plus 1, which is 3. And then negative 3 minus 2 is negative 5. 2 times u. So here I'm taking a1, I'm multiplying it by 2. And then multiplying b1 by 2. Or 4, negative 6. I doubled the length of this vector, of this displacement. Negative 3v, so now I'm multiplying both components by negative 3 for v. Negative 3 times negative 1, negative 3 times 2. And I get 3 and negative 6. So I flipped the direction of this vector, I reversed it, and I lengthened it, I tripled the magnitude, the length, the displacement. Finally, letter E, 2u plus 3v, very much more similar to the kinds of problems you'll see on assessments. I have a few steps I need to do. So first I need 2u. So we already calculated that up above. But suppose we didn't. That's just 2 times u, which is 4, -6. 3v. So note we didn't do this in part D. This is positive 3v, not negative 3v. So we multiply v by 3. -3, +6. And then we add it together. So 2u plus 3v is going to be 4 plus -3, and -6 plus 6, which is 1, 0. And that's it. I promise this does not get any more difficult than that. This does not get any more difficult than that. Let me know if you have questions. Again, please practice, and see you in the next section. Thank you so much.